Okay, that's good. Since we are working a very tight schedule in this evening, so I have better start right now for the chapter 5. But before that, please note the announcement. Now, today is the deadline for the submission of the assignment 5. Oh, by the way, can you hear me? Can you hear from me? Yes or no? Okay, good. Please submit the assignment 5, right, as soon as possible, not later than tonight, right, if you haven't done so. Now, since my workload is too heavy, so I may not reply you by receiving your email, okay? And please note the format of the submission, right? So A5, right? Your name and your student number, right? Student number and single file, right? In PDF format. So that's the file name, okay? So the file name, right? And please submit the assignment in a single file in PDF format. Please observe, right, my requirement. Otherwise, I will let you know to resubmit the file again. Please don't waste my time, right? And the second announcement is that please go over to the Blackboard and download the laboratory report guidelines, right? Now, there are many requirements, right, stipulated in that guideline. Please observe and follow the instruction as close as possible, right? These are the requirements. And you have to note the deadline for the submission in that guideline. So you have to submit the individual lab report, right? Not the group report, as I have told you earlier. Right? You have to submit your own lab report, right? By that deadline, stipulated in the guideline, okay? Now, let us kick off the chapter 5, right? Now, by the end of this chapter, you should be able to learn the basic concept and also the basic principle of the site investigation, sometimes called SI, right? Site investigation or the soil investigation. And then you have to know, to identify, right, the necessary ground investigation. You know, ground investigation is different from the site investigation. Now, we will go over all these aspects later. When you have done the ground investigation, you should be able to determine, right, the appropriate soil properties and also the site condition where the project is being undertaken. Now, site investigation is a process to collect the information, right, about the site, about your construction site. and is intended or is undertaken for the purpose of the future civil engineering design or the building development, right? In other words, both civil engineering and building project need this site investigation, right, for their planning, design, and the construction purpose. Now, what are the objectives of the SI, the site investigation? First of all, according to the Geo Guide 2 of the GEO, right, Geotechnical Engineering Office of the CEDD, right, CEDD means the Civil Engineering Development Department, okay? And you have to enable sufficient and economical design, right, with this site investigation results. Without the SI, your design may not be economical, right? And it could be coming across many engineering problems which cannot be solved unless you have performed the SI, right? So in the third objective, right, to plan the best method of the construction. So it's not only having to do with the design work, but also for the construction process. So that after the SI, you will be able to foresee, right, to predict what will be the problems and will there be any delay that could be arising, right, during the construction stage because of the ground or the local site condition. You may not know unless you have done the site investigation. And the fourth objective is to determine any changes that could be arising from the ground and the environment, right? And if you have taken notice of such possible changes, right, to your works, right, it could be not only in connection with the project yourself, but also the adjacent works around the construction site, the adjacent works or the environment, right? So with the same investigation, you could be able to tell, are there any effect of your project works, not only on the project building or the structure itself, but also any adverse effects on the adjacent building or adjacent properties surrounding the construction site. And so you should be able to advise, right, after the site investigation, you can advise any parts of your construction site or even the different sites, their suitability, right, in terms of the construction and also the design works. And to report the safety of the existing features and also the works. Here the works means the permanent structures, right, that you are going to construct, right? So it's a basic knowledge, right? It's a basic process which are important, which are crucial to the safety of the existing construction site features or also the project works. And also you will be able to establish any cause of failure of the natural features or the man-made structures, right, after this investigation has been performed. Now, what are the required information of a SI? First of all, the information could be related to the topography of the site, right? So it could be, you know, if there are any slope or are there any parts with, you know, high and low, right, elevation within your construction site boundary. So it gives you somewhat an idea, the topography of the site, right? the geometry of your site, right? Not only the plan size, but also the relevant elevations. And you have to know, right, any underground utilities, right, the buried surfaces, such as the electrical cables, water mains, and so on, right? And also the geological information, you know, the geology, right? Now, what's the history of the geology for your construction site? Are there any, you know, any surface deposit over some sand rocks, say some granite rocks, or even volcanic rocks, and so on? So you have to know a little bit about the geology or the geological background of your site. Right? Right? You know what's the geology? Geology means what in Chinese? Okay, 地質學. And also any period history of the site. Say, what's the history of the development in this site? Are there any previous factory buildings, or even the current building, or any chemical plants, or any toxic soil found in your construction site? Because if you have found those toxic soils, you have to do, right, some remedial work first, right, before the construction. Otherwise, your building could be built upon a toxic soil, right? Well, that is completely undesirable, right? It could impose a health risk, okay, a health risk to the inhabitants or the resident of your building. And you may perform the chemical analysis of the soil, right? You know, there's very famous pollutants called the dioxin, right? Okay, so you have to get rid of those toxic pollutants, right? And then, most important of all, for the 0.6 and 0.7, perform the laboratory test, right, for the soil sample, right, obtained from the site investigation. And you have to know the information about different layers of soil and rock beneath the ground level. And also, are there any groundwater, right, underneath? The procedure for SI, there are 5 stages, right? Test study, right? Preliminary study, main stage, construction stage, and post-construction stage. Now, let's take a look. Now, the test study start at the very beginning, right? During the project inception, right? Project conception, right? So you have to go to the computer, right, and search some knowledge and some information about the ground, right, for your construction site. And then in the preliminary stage, you have to perform the site reconnaissance, right, the site visits, right. So go to the site and take some photos and study the surrounding, right, around the construction site or within the site, right. And then you have to start to design the ground investigation, right, the borehole, right, the borehole investigation. So in this preliminary stage, you have to carry out this most important part, the ground investigation, right, to do the borehole, right, the borehole, right, the borehole here, right. And then Sorry. Okay, and then you have to perform the report after the ground investigation. Now, this report will give you the laboratory test result, right? The lab test results. From where you will know about the soil strength, right? The shear strength of the soil, right? And during the construction, you have to perform what? The monitoring, right? The recording, the actual ground condition, where you might need to do some further investigation, right? Before you complete the construction, right? And after that, after the construction, the post-construction stage, you may still need, right, post-construction monitoring. Well, it depends on the need, right? If there is any need, right, for the post-construction monitoring. Of course, for most construction work, we do not need this post-construction monitoring. Right? But for civil engineering, we do a lot of post-construction monitoring. Okay, now we go into more detail about each SI stage, right? The test study, right? You have to look for the geological maps, right? So you better visit the geo, right? The geo, where you can obtain the geological maps, right? To take out, right, what is the geological history of your construction site. And then you have to look for any previous, right, SI reports, right? Maybe there are some borehole already, right, already done around your construction site. So why not take a look on those SI reports and see, what are the soil layers, right, under your construction site. So this will serve as a very, variable, right, information apart from your own site investigation. So it could reduce the number of the boreholes, right, by looking at those previous borehole logging reports, right, next to your construction site. Right? Okay, and there may be some further geotechnical information published by the GEO, right? In particular, the Geotechnical Area Study Program. Of course, this could cover, right? It covers a much larger area, right? Say the program, right, may give you some information, right, on the geological aspect for a Moncourt area, right? But your project size only is a small part within the Moncourt area. So, but anyway, these gaps, JSP, could be beneficial, right? In addition to your own site investigation. And also you look for the UU, the underground utilities, right? Any electrical cables, water mains, telephone lines, and so on. And also you may take a look on the aerial photo, the photo taken from the airplanes, right, flying over the site, right? So it gives you an idea, right, from a view, right, over the sky, right? So you have a burst view of your construction site. Now this could give you a 3D image, right? By using special device, you can obtain the 3D image, even though from the 2D right aerial photo of the site. And also you should the test studies should cover right what are the past construction records around your construction site, right? Now, all these are the test studies, right? Like the site reconnaissance, right? The site visits, right? So you should go to the site and have a visual inspection, and see are there any existing slope, are they dangerous, right? And any buildings around, are the buildings truly vertical or already tilting, right? Or are there any rock outcrops, right, from the slope or from the ground? So you can have a look with your eyes, right? A visual inspection. Of course, you can take photos, right, for later reference. Now, the procedure of the SI, the main stage. Now, this is the most important stage. I think that is the most important stage. Because you have to perform here the ground investigation. Sometimes it's called the site investigation is not too correct, right? The site investigation should include those test study, the site visit and so on. So better not use this word, site investigation. Here, right, we call the ground investigation because there's the ground, right? You want to know what happens below the ground level. So that's the ground investigation, the GI, right? It's the purpose of the GI, right? To identify and to discover what are these different soil layers, right? What are they, right? Are they soil or rock and so on? Or sometimes you have to carry out the special study, right? For the disposal of material or some, are there any toxic material, right, left behind, right? Because some factory may have been moved out and they have left some toxic material behind, right, or even below ground level. So you have to do some special study. Now, the construction stage. After the ground investigation in the main stage, usually the information may not be that sufficient, right? They could be quite limited. So when you open up a site, right, because you are carrying out the construction work, so you are doing the excavation, say the open excavation. Sorry. Right. During the excavation, what you are doing is to open up the ground, right? Open up the ground. So when you open up the ground, so you may be able to obtain more information about the ground because you open them up. You are doing the excavation, right? So this information could be, serve as additional or much more variable information rather than the GI, right, where you just do the boring, right? And then you will able to review, right, all the information collected previously, and you have to carry out the monitoring, right? Example, the groundwater pressure. Are there any seepage of the groundwater from the slope? Or are there any settlement of the structure somewhere around, right? Are there any lateral movement during the construction, say the retaining wall or the adjacent building and so on? And by having this additional information, you will be able, right, if there's a need to amend your design or the construction procedure. Now, the design and the construction procedure could mean for the permanent works, right? The permanent structures, permanent building, and also temporary works, right? Temporary works. Okay, so this information could be very variable, right? If you obtain all this information during the construction stage. Post-construction, although it's quite rare, right? Quite rare. I mean, rare in building industry, but some in civil engineering, right? Civil engineering. Say for slope, right? For a very high slope, high and steep slope, where you may need the post-construction monitoring, right? Say for a bridge, you may have to monitor the vibration, right, of the bridge and so on. Okay, now let's come to the GI, right? It's a very important topic, as I have told, right? The GI, the ground investigation. Now we want to know the character. What's the nature of the soil, right? Below the ground level, right? What's the underlying soil are, right? Are they very soft or even a very medium or dense sand or clay and so on? So you have to know the character, the type of soil and how they vary below the depth, right? The variability of the ground and also the groundwater, right? Now, the extent of the GI will depend on how complex they are, right? If the soil is expected to be very complex, then you have to do more borehole, right? And also, it will also be affected, right, by the type of project. Say for very big project, then of course you need more borehole, right, in the GI. And also, we are talking about how much information are available at your hand. Right? If you got a very good deal of borehole information around your site, that means you do not need to do more boreholes, right? Because you have already got a lot of information. But you know, for a very remote site, right? You do not have any, you know, the GI reports around your site. Then in this case, you should perform more boreholes, right? The extent of the GI could be much greater, right? And the GI, you can see this important word. Right? What's that word? The boreholes, right? The borehole, right? You make a hole into the ground, right? By drilling, right? Drilling a hole, right? Sorry. Drill holes, right? Or to bore the hole. Right? Now, the location and the number of the borehole should be very carefully planned. So, for a construction site here, this site, if you know there's a column there, there's a column there, right? So you should not bore. You should locate your borehole right here, somewhere here, right? And not at the corners, right? Right. So you better put a borehole there, right? Because you want to know, right? What are those soil beneath your column, right? Or, you know, so you have to perform, right? A borehole there. So better borehole there, right? you should not do a borehole there, right? It's useless, right? We want to move the borehole, right, as close to our column as possible, because the column will eventually be support the foundation, right? So we want to know what sort of soil, right, beneath the column. So you better plan a borehole close, right, as close as possible to the column positions, right? Because they are the position of the deep foundation. And what are the spacing? It's about 15 to 30 meters, right? So, you know, that is borehole, right? So 15 to 30 meters, right? And what about the depth? Well, it depends on what's the foundation depth, right? If you got a building there, right, and then you got, you know, the piles there, then you have to do the borehole, right? Right, the borehole should be deeper than the foundation, right? You should not do a borehole just at that level, right? You don't know what sort of soil, right? You don't know the you know, the information of soil, right, below the foundation. So it depends on the foundation, right? The depth of the foundation you are going to design. Okay. Now, in determining the depth, the depth of the borehole, there are some, you know, important remarks here, right? Now, all affected soil should be considered, right? In other words, if your foundation is placed over a certain depth, so you have to know that soil, right? So you have to do the GI to discover, right, and to collect samples, right, at that depth, so that you know whether that soil will be able to support your structure or not. So all affected soil need to be investigated. In other words, if you have a pile there, this soil, right, must be investigated, right, because you are using the soil to support the foundation. And what about if it's rock? If there's a rock, there's rock. Now, according to the geo guide, you need to drill the hole for a further 5 meters to establish is a truly rock or not. In other words, if you drill a hole 5 meters, then you can stop here, because we assume that that must be rock, right? So anything for 5 meters, if that is rock, then we believe that the whole thing is rock, okay? Now, you don't need to drill for, say, 10 meters or even 20 meters and so on, right? So for anything more than 5 meters, it should be a rock stratum. Now, of course, if you right, that's if you perform, right, here, right, 3 meters, and then you come up to the soil again. So that should be a what? A boulders, right? Okay. So for a depth, if you find the rock, right, extending over a depth more than 5 meters, then it must be a rock stratum, right? A rock layer. anything less than 5 meters, it could be a boulder, okay, a big boulder. Right? That is why we have this requirement, right? Drill into rock, right? 5 meters to establish is a bedrock. It's a bedrock, right? It's a rock formation layer. Okay. Now, what about for the depth of the foundation for a shallow foundation? Suppose there's a shallow foundation. Okay. Now, if the width of this foundation is B, okay, say B is equal to 5 meters, then you have to do the site investigation up to a depth of what? 1.5 times 5. So you have to do the boreholes, right, up to 7.5 meters, right? At least 5 times, right? 1.5 times of the depth of the breadth, right, of the width of the foundation, right? That's the B, right? 1.5 times the width of the, the foundation for shallow foundation. Oh, sorry. What about for cut slope? For a slope, right? Suppose you have a slope here, right? Then you have to do the borehole, right? Up to what? 5 meters here. Say the original ground here, the original ground here. So you have to do the borehole, right? So the height of slope plus 5 meters, right? So you have performed, right? Here, right? The ground level, right? To do the site investigation up to a depth of the height of slope plus, a 5 meter below the toe of the slope. So h plus 5 right, meters, where h is the height of slope. So let me check out whether you could follow or not. Could you follow my explanation of the lecture notes? Yes or no? Okay. Now there are some, photo about the site investigation, right? So you could have some, digging a big hole, and then you go into the bottom of the, this well or the pit, and then you should check closely, right? What sort of the soils are there, right? If you are a geotechnical engineer, you should be able to tell, right, from the face exposed from these 4 walls of the pit. Then you will learn about what sort of soil, right? Are there any loose soil at the top? And what about other soil, at this level are very stiff, or are they very wet? Are there any groundwater? So you should be able to tell, right, from the pit where the soil are exposed to your eyes, to your naked eyes, right? And even you can touch, the soil, and use your hand and fingers, right, to have a feel for the soil. Are they very, very sandy, or are they very soft, or they are clay or sand, right? So you can do a lot of investigation there. Right? Now here is the setup for the the machine, right, to do the borehole. Right? You can see here, right, a motor there, right, a motor, right? And then you have the the drill rock, right, the drill rock, and here's the diamond bit, right, The diamond bit means, you know, the teeth, right? Right? Because it's rotating, right? So it can cut away the soil, right? And drive into the soil. Okay? So that is a typical plants, right? For the drilling, what we call the drilling rake, right? The machine, right? A very simple machine, right? With a motor and make the rock drilling, right? With the, you know, that diamond bit, okay? Now we will go into some detail about the, you know, the drilling rock and also how the sample are collected. Now there are two methods. Open hole drilling, right? So it means that, right, open hole drilling. So you use a machine, right, to take this soil out. Okay, that's an open hole, right? So you got the hole there, right? With the machine, you're digging the soil out. So that's open hole drilling. Right. Now, in Hong Kong, we prefer a much more reliable and accurate method, the core drilling, right? Right, the core drilling. Of course, during the drilling, you have to apply the water, right, to washing the soil out, right, washing the soil particles out. So the drain fluid is the water. Right? So we will talk about the core drilling. Now, for the open drilling, you can see here there's the ground, right? And you take this soil away. Now, this gives you a very disturbing, right? Because you are driving, right, your rock into the ground. So the soil here will be disturbed, right? So it will lose all the properties, right? Because it has been disturbed, right? Disturbed. So that's no good. Disturbed sample. Now, for the core drilling, you can obtain the what we call the so important undisturbed sample. Undisturbed sample. How can it be done? Now I try to explain. All right. Say here, you have a casing, right? A casing with the teeth, right? And then it's rotating. So, but on the other hand, so it come to this level, okay? Okay, this soil will be out, right? And then inside there will be a core, right? A core tube, right? Which is pushed into the ground. Okay, you stop the drilling, right? So, right, you come to that level, and then you use this, press this tube. So this tube will go into the, say, 1 meter, right? So it's pushed below this ground level, right? Now the upper part of the soil about this level has been, you know, excavated away, right? But here you push this inner tube, and you and then take it out. Now this is undisturbed sample, right? Because it hasn't been disturbed, because all the operations stop at this level, right? Here, at this level. Anything below will be undisturbed. Anything above that level will be disturbed, right? So that's the disturbed. The above, right? Above part, right? The above part has been disturbed, but below this part, it will be undisturbed. So you try to, that's what we call the core drilling, right? So you have a core sample, right? A core undisturbed sample to be taken away, right? So sometimes it's called the sampler, right? Core sampler, a device to collect, to pick up the samples, right? Of course, you have to stop the rotation, right? And then push, right, the tube, right, the open-ended tube into the undisturbed soil and collect the soil sample. So you have to stop the operation, right? And then you have to push, right, the tube into the ground to collect and pick up the disturbed sample. Of course, this will be a slow process, right? For the upper part, right, where you are performing, the continual disturbing, right, the soil, of course, it will be the open hole drilling will give you a much faster advancement rate. So we have these two, right? For laboratory tests, of course, right? We want this undisturbed sample. It gives you what? The shear strength, and also the, any consolidation test. For disturbed sample, you cannot have a correct, right, testing of the soil shear strength, but you could able to tell, right, the classification, and whether there should be a clay, the soil particle analysis is okay, right, even after disturbing, right? So what are the percentage of the clay particle? What are the percentage of gravels and the sands and so on? Well, it doesn't matter, right, for the disturbed sample. But regarding the strength, you have to obtain the undisturbed sample. Okay? So you can obtain the disturbed sample, but you could also they use the sampler, the split tube sampler. It means that, right? Okay, this is split, right? The split. Split tube sampler, right? Whether you can, after you take out the the sampler to the ground level, and you split it up, right? And then you collect the soil sample within, right? Here the soil sample, right? So after you splitting the sampler into two pieces, you can take out the sample, right? The soil sample, right? Of course, you may obtain the the block sample in a trial pit. You know what's a trial pit? 探井. So you ask the workers, right, the laborers, right, to take out a backhoe, right, and then at the bottom, right, you can take out a block sample, right? Here the block sample. And we have different quality, right, of the sample. Here, the best one, the best, class 1 and class 2, right? So for, class 1 sample, you can carry out the strength test, right? The strength, right? And deformation and so on. A lot of tests for class 1. And for class 2, you could have some moisture content and density test, but for, the poor quality, right? Only for eye inspection only, right? For visual inspection only. So you can tell from, the class 5, the only information is about, right, the nature of soil, right? Whether it's rock, whether it's rock, right, soil, right, and the minerals, only that, right? Only that kind of information for the class 5, right? You cannot perform any tests, right, for this poor quality sample. Now in Hong Kong, we use the sampler tube, a very famous sampler tube. It's called the Mesa Sampler, right? The Mesa Sampler. It's about 74, right, millimeters in diameter, right? Right? It's very suitable for the, soil triaxial test. For the, if you got a Mesa sample, again, it's a, a split sampler. So after you are splitting the shell out, and then you could, cut it right here. Say it's about 1 meter, right? 1 meter long sample, and then you can cut pieces, right? So you obtain, right? Here, right? You got this, right? 74 millimeters in diameter, right? 74, and then you can apply the loading, right? Of course, you could have, so the XY and the Z-axis triaxial test, right? So what we call the sigma 3, and that is sigma 1, right? Remember that? Sigma 3, and that is the sigma 1. You can draw the Mohr circle, and then you can obtain, right? That is the C cohesion, and that is the phi, okay? So we perform, right, for a series of the, so that is, that is, the sample 1 and sample 2. You can have, many samples, right? So it's quite expensive to do the laboratory test. First of all, you have to obtain, right, several undisturbed samples, right, from a certain borehole log, right? And also at different layer, at different depth, you have to collect different, soil samples, right? So the total cost could be quite expensive in terms of collecting the sample during the borehole drilling, and then the triaxial test for these samples, right? And then you have to work out the analysis and what are the, the cohesion and the friction angle and so on. So you have some idea, right, about the, this one is the, here, right here. It's about that, right? The rotating, the drill bit, right? Okay. And then here, right, is the sampler, right? Sorry, here, right? Now, let me tell you like that. Okay. Now that's the inner tube. Okay. Now what about the outer one? Now the outer one. Sorry. Okay. Now the outer one is rotating, and here, in fact, you can imagine there are a lot right here. Right? So there are the steel bearings, right? Now the outer one is rotating, right? But the inner one is stationary. It's not moving at all because the movement will be guarded against by this, called the ball bearings, right? Ball bearings. Remember, the outer one is rotating, but the inner one is not rotating. So it's important to collect undisturbed sample with that sort of machine. Right? The external one is rotating, but it will not bring the inner tube rotating as well. In fact, the inner one will be stationary. That's the important concept for the core rotating drilling. Right? So can you got my idea? Right? So you understand what I'm explaining to you? Okay. Now we come to the, the sampling the ground. Okay, sampling the ground. The frequency of sampling and testing. You mean how many samples should be taken and what sort of tests will be performed, right? Well, it depends really upon how many information you have got at your hand. Right? If you do have a lot of information already from the site investigation report, right, made in the building around your site, so you don't need a lot of sample, right? And you don't need too many boreholes, right, to be drilled. So it should be a balance, right, between the effort and the information you have got, right? Anyway, right, for the in situ weather rock, what's the colloidum and some fill material, right? So, here's the ground level. Now, usually, because of man-made activity, you have already performed a lot of the filling works, right, previously, right? The fill, the man-made fill, it's not natural, right? The man-made fill. So it's quite loose here, right? Then you should, at the top, right? You should do some sample, right? You should do in collecting some sample, right, in the top layer, right? So that's the fill. What's the colloidum? You know what's the colloidum? Say here, right? It's a hill, right? So that is the soil one, certain type one. But sometimes we find some rocks, right? Rocks. It should not, right? Nothing to do with the soil type one. It's the type two. Right? Why is that there? If that rocks, right, comes from the soil, so it should be type one, the weathering, right? If the rocks is weather, we can identify, right, the soil and the rocks here are belonging to the same category, right? The type 1. But what about if we find there are some rocks of type 2 different from the soil underneath? So we understand it should be the rocks coming to this position from somewhere else, right? So it's the colluvium. So it could be blocked all along, right, by the water, right? Say there's some water, right, carrying the type 2 rocks from somewhere else. So, and then eventually it stayed there, right? So 叫沖積土啦。So if you have find, right, if there's a layer, right, consisting of, you know, some rocks type 2 different from the soil underneath, or the rock type 1, so there's a layer of the colluvium here. So the colluvium is quite dangerous, right? Because it's not stable, right? It's not stable at all, right? This layer of soil is not directly weathered from the rock beneath, right? In fact, it has been coming from somewhere else. So it's not, the strength of the colluvium is very, you know, soft and low. It's not stable. So you have to collect more sample about this colluvium. And then we perform the Spt test, right? The Spt test. Standard penetration test. Okay. Now we will go to the Spt somewhere later, right? Now groundwater. Groundwater means, you know, the depth of groundwater. Right? Say here, this is our ground level, and there's the groundwater table there, GWT, right? So you want to know what's the depth of the groundwater beneath the ground level, right? It's very important. Right? You can have the stem pipe, stem pistometer, or hydraulic pistometer. Now, you don't need to study too details, right, into the construction of this pistometer or stem pipe. Now, let me just take a brief look, right, for this field apparatus here, right? Now, stem pipe means what? You drive a, you know, a PVC pipe, right, with many holes, right, perforated, right, perforated, and then it's a hollow tube. If there's groundwater table, so you measure what's the depth of the groundwater there, right? So there's a stem pipe. So you directly drive, right, a perforated PVC tube down into the ground. If the water comes inside the tube, and then you can measure the water level there, right? Now for the open hydraulic pistometer, watch out this. Right? You have, right, the sand filter here. In other words, the water seep into, right, there through a filter, right? Filter. It will not get clogged, right? Don't get clogged for the perforation. Now in the open tube, when the water, right, go into your PVC tube, right, for some time later, the soil particle may clog up all the holes there, right? But here we have the filter, so it's a better design. And also you can see here, bentonite. So it's sealed. It got sealed at the top and bottom. So any water, right? You are measuring the water level changes here, from here, right? depending on the design, so you can have the fluctuation level. So that may affect your, the length of the filter required. Okay. You can see here, right? You can see the, the filter there, and you get, the upper part clock, right? Block up, right? And also here you block here, right? So any water level will be changes between this level, right? So that is the groundwater table, right? Changes here. Okay, now there are quite a number of tests that can be performed within a borehole. So during the site investigation, you could have the SPT test, right? SPT test, standard penetration test. Now, let me explain what's SPT. Now, SPT means that now when you drill, right? That is the, that's the, ground level, right? Suppose you are drilling up to this part. Okay. Okay. Drilling up to that, and then you stop drilling, and then hammer. Okay, you got a weight here. Now this weight will drop a certain distance. It defines the distance, right? So this H is fixed, and this H is also fixed. So a certain mass will be dropped through a height H, and then under each hammer blows, right? Under each blow, you will have the penetration, right? The penetration under each blow. Under each blow, right? And then you record the blows. And then you have to report for a penetration 300 millimeter. What's the number of blows? It's number of blows, right? With the given hammer of fixed weight and dropping through a fixed distance to give 300 millimeter penetration. Because the SPT value, okay? It's the N. N is the SPT values. So if inside a borehole log report, you notice that N equals to 13. What does that mean? It means it requires 13 number of blows to give 300 millimeter of penetration, right? That is the SPT value. So you can see the SPT value here. Okay, the SPT value. SPT, right? Now, here's the borehole log. Sorry. Well, for the borehole log, right? So that's the borehole number. Right? Here's the borehole number. And then, the date of the borehole. And then you have, the the depth, right? Here's the depth, okay? And then you have the reduced level, you know how many meters per MPD, right? Okay. Now, that's the depth. Now, for each different depth, you can see here's the description of the material, right? Okay. So, and it's quite difficult to read here. Right? You can see here, right? Right? Loose, right? And gray color, right? With cobbles, right? So this should be with fill, F-I-L-L, fill, right? Fill. So this is a mimic fill. And then you could, you know, here, right? You can see here, you know, you can see here the wick, right? Yellowish, right? Granite, right? It's the granite. Now all this description should compile with the GEO recommendation, okay? Now, and you can see the RQD, right? It's the rock. Now RQD, say 100% means that you got pieces, right? Right, 2 pieces of rock, right? Taken out from the borehole. And then the recovery, 100% means that when you got, say, here 400, that's 600, so give you 1,000. So when you pack 2 pieces together, it gives you the same, like total length equal to the original length of the sample. So the recovery is, you know, is 100%. But what about that? If that is, you know, 300, right? And next day is, you know, 600. So you got a sample, right? 1,000, but you pack 2 pieces together, you got only 900. So 900 over 1,000, it gives you recovery, 90%. So there are some gaps there, right? So you have joints, right? The joints. So for very good rock, the recovery, the RQD, right? Okay, should more or less 100%, right? It's a good rock. For a very low value, say 70% or 50%, that means you got a lot of joints, right, in your rock. That's no good. Right? Okay. So that is to know. We have briefly discussed. All right, discussed. How to read, right? Here, the borehole log sheet, right? Okay. And you can see here, you know, what's the, you know, that sample, the sample is taken, right? The sample taken. It should be about 1 meter, right? 1 meter sample taken. What are these samples? You can see the legend there. Right? The SPT, right? The SPT sample, right? Okay. So I better hurry up, right? The site investigation report. What is a site investigation report? It consists of 2 parts, right? here, right? The descriptive part, right? Regarding, the briefing of the procedure employed, how the site investigation has been performed, and what sort of data you are going to obtain, to collect. And then the second part is the most important one, how to analyze the data and any recommendation and conclusion. For instance, right? What's the cohesion, C, phi, gamma, and so on, right? Or the groundwater table, right? Now, all these are the important result after the analysis. So for the, this guy, very famous, M.J. Tomlinson, right? Famous guy for the foundation design. Now, he recommended a typical site investigation report should include the following, right? The introduction, the site description, the geological background of the site, and what are the soil condition, right? Description, and what are the test results, and then how they are analyzed, and any recommendation, right? And the conclusion. Now that could be an important, right, information for the foundation design and construction work. Okay. Sometimes you may include some, the geology about are there any, particularly in the rocks, the fault, right? Are there any faults, right, found within the rock formation? Or even any, the cave-ins? The karst. Do you know the karst? Right, the marbles, right? 溶洞. So they are very important, geological information, right, from the site investigation report. Okay. So the description of the soil, right, here, right? The soil condition, and also in the borehole logs, and the section of site, right? If you got a borehole, right? So you got a borehole 1, borehole 2, right? Borehole 3. Now suppose, right, it give you a rock depth here, right? Say 30 meters, but here the rock depth not 30 meters, 32 meters, right? And here you got, right, 35 meters. So the layer of the rock layer is not horizontal, right? It's a bit tilting, because you can see here it should be sloping, right, from this direction to this direction, because the depth here, right, is 35 meters, but it only appears 30 meters here. So it's not a horizontal rock stratum layer, right? It's an inclined one. So you know the section through the site, right? Okay, and also the laboratory test result. And some discussions should also include the description of any main structures, right? And also the description of the main structure and the related loading together, and in relation to the test result, right? What does that mean? So this description should give you, right, a discussion, right, should give you an idea, right, the lab test result, how they are tallied with the foundation design. So, right, that building here, right? So the, if the building is going to, right, to be founded on these rock layers, right? You have a very quick loading, right? So you're expecting what sort of the, the rock pressure here, right? Now, according to the test result, right, it should be much less than the rock capacity, right? In other words, the rock should be able to support that rock pressure, or in other words, to support the height of the building above the ground level. So the lab report should give you, right, a good discussion for that, right? Whether the rock stratum or the soil stratum is able, right, to support the building through the foundation. Right? So finally, you have the recommendation for the foundation design, and also any, the monitoring required during the construction or even after construction. Okay, so that's end up our site investigation chapter. Right? So any question? Any question for this chapter? Are they clear? Are they clear to you? Yes or no? Now, I will recommend you to do, more, right, revision on this chapter, because I have, will you excuse me? I have to, to do the lecturing in a rush, right? Because we're running out of time, right? So I have to explain the main themes, right, under each slide of this chapter, right? Without going into the too much details. I'm sorry for that. Okay. How about the others? Is that okay for you? It's altogether 20 something here, right? What about the others? There are only too few to respond my my question. I want to have some more feedback from you, right? Rather than few. Okay, then I will stop the sharing here, because I have to move into a new chapter. Chapter 6. Can you see the chapter 6? Okay. Now, chapter 6. The site formation. Have you ever heard about the site formation? Okay, 地盤整理 site formation. The learning outcomes under this chapter will let you to appreciate, right, the basic principle of the site formation. and also what are the requirements of the site formation. In Hong Kong, in Hong Kong, the earliest settlement in Hong Kong is somewhere around in the central, right? Central of the Hong Kong island. And then the government, right, has settled some people living in the Kowloon Peninsula, right? Peninsula, right? And then government will start to decentralize the population living around the Victoria Harbour. So they have to develop, right, a new site, first in Sam Shui Po, right? And then later, it's not good enough, right?長沙灣、荔枝角, and then go to new territories, right? The first is Tsuen Wan, right? And then you have the Sha Tin, and then Tuen Mun, right? And then what? Cheung Kwan O, right? And so on, right? And then Dong Chong, right? Dong Chong, and so on. Now we come to what? Hong Shui Kiu, and so on. Now, we are talking about the new town, right? New towns, 新城市鎮, 新市鎮. So we need to do the site formation. So within each new town, we have to do a lot of site formation work. First of all, you have to clear the site, right? The site clearance. And then you balance the cut and fill. Say here, you know, if that is, you know, that is Tsuen Wan, right? That's the Dai Mo Shan. And then that is to know, that's the, here's the sea. And so you have to what? To remove some part of the hill here, right? You got the soil, right? And put it here, right? To reclaim the land. You know what is the reclamation, right? You heard about the word, right? Right? The, you know, cut and fill, right? Fill. Sometimes if you put the fill over the seawater, it's called the reclamation, right? Okay? Cut and fill. So it gives you what? Two pieces of flat land. You got the flat pieces here and also the, you know, the flat pieces of land here. So it's good for you, right? You want larger pieces of, you know, flat land, right? To build the houses. So by cut and fill, you are creating more land areas, right? For the housing, for the town development. So what that is called cut and fill. And of course, you have to do some additional work, right? What? The road system, right? The road system. Now, during the site formation, we will talk about the excavation, the watering techniques, the roads, and also the landscaping works. Okay. Excavation. You know what's excavation? To dig the soil, right? Cut the soil. Use the machine, right? Cut away the soil. That's the excavation, right? So the next job is to fill, right? Right, place the fill, place soil, right, over an area, It's called the fill, right? Cut and fill, right? You want to balance it, right? You balance it means you what? For a site, If you got, you know, say 1 million of cut, and then you put it here, right? You got 1 million of fill, right? 1 million cut, I mean cubic meter, right? 1 million cubic meter of soil cut away, and you put that 1 million cubic meter of soil into another area to fill up all the space there, right? So you don't need to, right, cut away, or you should import the fill. Here you always use the money, right? You spend the money, right, to cut the excavated material away, right? If you are filling too much, then you have to buy the soil, right? To buy the soil, right? And to be placed in your filling area. So you better balance between the cut and fill. Then you don't need to pay any money at all, right? So the idea is to balance the cut and fill. Right? Now, for any cutting or filling works, you have to make sure there will be no instability to occur, right? So you have to make sure what? The cut and fill will be able to stand on its own, right? It should be stable, right? So cut slopes should be stable, fill slopes should also be stable. Now, the excavation equipment, the bulldozer. You know what's a bulldozer? Here is the bulldozer. Now, it's called this, it's a blade, right? Blade. 刀片. So the blade with teeth, right? With some teeth. Right? Or sometimes without, okay, without teeth. So it's a blade, right? It pulls, right? Now, it is going to, right, to push the soil away, or sometimes you have to do some, what we call the trimming, right? Trimming. Level trimming. Suppose you got a surface here, right? You use this blade, right, to trim the soil, right? Use the blade, right, that give you a very smooth surface, right? You use this, you know, this blade. This soil will be moving out, right? To move out the soil, right? To spreading and moving the material away, and then trimming to the correct site formation level, right? Whether you can construct the road system and so on, right? So that is the purpose of using bulldozer. And they sometimes called the loader, right? The loader. Now the loader can do the excavation, right? You can see this machine, right? First, you know, cut or excavate, right? You can see the teeth here, right? It could cut, right, the soil, right, from a mass of rocks, or a mass of soil, and then you have to the lifting, right, and put it, right, disposed to trucks, right, okay, or the lorries. So it's a very strong and powerful machine, right, to do the excavation, the lifting, and dispose the soil, right, into the trucks, where the trucks will move the, you know, the mass away, right? What about the backhoe? We see a lot here, right? Here in Hong Kong, to do the trenching work, right? The backhoe, right? Now all these sometimes on wheels or tractor, right? You know what's the purpose of wheels, right? The wheels means here, right? Sorry. The wheels, right? And these are the tractor, right? The wheels are much faster, right? For faster movement, you use the wheels. But for soil, you use the tractor, right? Okay. On hard surface, it's good to use the wheel on hard surface, right? Just like on the road carriageway, right? And the trucks for cutting the material, right? The dump trucks. Now we come to the soil permeability. Now in soil permeability, we are concerned about the seepage. Right? If you got a site here, right? There's a ground level, and if you got the groundwater table, what will happen? Right? So the water will be seeping. Right? We have the seepage. Now, depending on the soil properties, right? The soil is the gravels, right? The larger size soil particles, the gravel. What about the clay? Right? For gravels, you have a very serious seepage, right? Seepage flow, right? And for clay, right, you have very small seepage because the particles are too fine, right? So depending on the nature of the soil, so we have to, to study about the permeability of the soil, right? So it performs very different, right, between the gravels and the clay. Now, for studying the soil permeability, we have to know the Darcy law, right? The Darcy law. The Darcy law, right? Now, it's equal to the, the I hydraulic gradient times A and times the coefficient of permeability. It gives you the cubic meter per second, right? Okay. So remember that, right? Say, if you want to know, right, how many water will seep through an area. So that's A, right? You want to know what's the flow rate across this area that has been seeping through. So you have to measure, right? If the water table is here, right? The water table is here. Because there's a difference between the water pressure, right? Downstream and upstream. So that is a difference, right? So that's the difference in the water pressure. And if that is, if that is L, so the hydraulic gradient is equal to the what? delta H over L, right? That's the hydraulic gradient. You know, the difference in the water pressure over a length of the soil, right? So that is the I, the hydraulic gradient. And then we times that hydraulic gradient with the area A, and times the, you know, all these are the, you know, the geometry only. Then you have to multiply, right? A soil constant called the soil permeability, right? The coefficient of the permeability. Now that will give you the flow, right? Remember this equation, right? Q equals to permeability coefficient times the hydraulic gradient times the area A. Here, for this table, for gravels, right? Q equal KIA. So if you know, if it is a, you know, a big value, this Q will be big, right? So you can see here, right? The K, right? The K here, right? So for gravels, right? The K value is very large, right? 1 to 100. What about for clay? You can see the clay very small, right? 10 to the power minus 10 or even minus 6, right? So it gives you a smaller K value. So smaller K will give you a smaller quantity of flow, right? That can be sipping, right, through a mass of soil. Of course, the soil permeability is having to do with the particle size, and also is regarding the voids, the size of the pores or the voids, right? The void continuity, right? And also of this, right? The physical characteristic. For this example, right? From A to B. So you consider, you know, so here the A, right, to B. Now we want to know water flows from point A to point B. Then you have to know, right? That should be at a higher water pressure, lower pressure, right? And if it is 15.5 meters and that is 10.2 meters, right? What's the difference? So that is the level difference. So delta H equals to what? Minus 10.2, right? So it gives you this one. And what about the L? Delta H over L. L is what? What's the distance between A and B? 8 meters, right? So it gives you the hydraulic gradient, right? Delta H, and that's L. So it gives you that. So that is the I, right? That's I, right? That's the K, right? What's the area? 0.5 meters square. So it gives you the, you know, the quantity of flow, right? Now you can have two types of tests for the constant head method or the falling head method. Okay, now we come to that. Now that's the constant head. Now constant head means what? When you have continuous supply of water here, right? And you have an overflow pipe. So for any water, it will be always maintained at this level. So here, right? You can see here, right? The that is the soil sample, right? So what's the head here, right? H1 is equal to what? Right, that's H1. Right, that's H1. Now, any water going out, so you got what? Here. Right, is equal to what? 0, right? So the change in the water pressure is this one, H, right? So if that is H2, so it's equal to H1 minus H2, right? Anyway, it's the difference, right, between the water levels and this water level, right? So that is the hydraulic gradient, right? H over what? L, right? Is the sample. And K, I, A is the sample, right? So it's equal to the, the amount of water, right? Amount of water, dW, is the amount of water collected over a period of time. Okay? You have dW, right? Cubic meter, right? Collected over a times interval T, right? So you got this Q, right? This is the Q, right? The quantity of water collected over a period of time, T. So you can work out the K by measuring the dW and in terms of say 5 minutes or so. So you got this laboratory data and you got the area A and H, right? You can measure the difference between the water head and the length of sample. Then the only parameter is Q. So you got this equation. So by measuring the dW, L, A, T, and H, then you can determine the coefficient of permeability for the soil sample there. Okay. Now we come to the falling head. Now falling head method is somewhat different, right? Now it allows T equal to 0. And then you allow the water dropping, the water level dropping, right? Say T equal to 1 second, it comes to here, or 1, or 2, come to here, and so on, right? And you measure, right? Say for, that is the T equal to 2, right? T2 here, and that is the, the T1 here, right? So from time T1 to T2, you measure the, the H1 and H2, right? The distance between this level and the water level, right? So that is T equal to T1 and H2 is T equal to T2. Then you input this, the data here, H1, H2, and you got, the A is the area of the pipe, right? The A is the area of pipe. Here, the A, sorry. The pipe, okay? And the A, big A is the area of the sample, right? And T is the time taken, right? Recorded for the responder amount, right? From T1 to T2, right? So T equals to T2 minus T1, right? And then you got this formula, right? Of course, you may wonder how this equation come. You can use the calculus, right, to work out this equation. Now, I will not bother about the derivation of this equation. Okay. Now, of course, in the actual site formation, the laboratory test never give you a very accurate result because in the field, right? In the field, we have the different boundary condition, right? In the lab, you got a tube, right? But in the site, it's not a tube there, right? Right. So you also may not simulate the actual concurrent data. You are conducting a test, right, for a test soil sample of a certain thickness, right? But in the site, you have layer 1, layer 2, and so on. You may have multiple layers of soil. How can you use this sample, right, to represent the actual site condition? So that's why we use the, the field test, right? The field test. Well, in field test, I will prefer to use the, the pumping test, right? Here you pump, right? You pump some water, right, into it, right? So the water is going out to pump the water out. Right? You got the here. When you pump the water out, the water level, right, will go down, right? So from T equal T1 to T2, you measure, right? You use the, some instrument to measure the water level, right? How much the water level go down, right, within a certain period. Then you can apply the formula, right? The falling head test formula, right, to work out the actual coefficient of permeability, right, for the in situ soil. So that's the pumping test, right? And sometimes you can here, right? You continuously, pump the water out. Use the pump out. So you install, right, the 2 wells, right, next to your pump site. And then you measure the water level, right? Of course, the water level in this well close to the pump, you got a lower water level, and further away from the pump site, you got the original groundwater level. Then you measure this H1, H2, and then you apply the formula. You can work out what's the K, right? Now that's what we call the confined aquifer. What's the confined? This is impervious, right? In other words, this soil is, permeable. 個透水層啊 and the upper part impermeable and impervious, right? That's the confined aquifer. Of course, you may have the unconfined aquifer, right? In other words, here, right? You got here, right? Pervious, while the lower one is impervious, right? Again, you can apply different formula to work out decay, right? Now here we go. In confined aquifer, you use this formula, right? Now these are the observation wells, right? You take the reading. Now these are the, now these are the observation wells, right? To observe the water level. And you got R1, R2, right? The distance between the well to your pump site, right? Or pumping location. So for confined aquifer, you use this formula. For unconfined aquifer, you use another formula, right? Well, dewatering. You want to keep your construction site dry. Sorry, we have just disconnected. Can you see the PowerPoint now? Okay, good. Okay, dewatering. Now, dewatering is going to keep the construction site dry, right? To keep the site dry, okay? That's why we have to pump the water out of the, say, for excavation site, say in a basement construction, right? We never want the groundwater, right, go into our site. So you got several methods, right? The most common one is the open sump, right? The open sump, right? So you make use of a hole there, a pit there, right? Sump pit, sometimes called sump pit, right? Sump pit, and you lower, right, a submersible pump, and then to pump the water out, right? Water. So you keep, right, this groundwater table, right, below this point. So the site here is dry, okay? And you could have the watering well, right? What we call the well point system. Well point. Okay? 點井. Now, by drawing the water, right? Pump out the water, right? The water level, the original groundwater table could be here, right? Now it come to here, right? We call the drawdown, right? So this is the drawdown of groundwater table. Now, if you use the suction pump, SUCTISO, vacuum pump, right? 真空 pump. Now, the drawdown is about 6 meters only, right? It's less than 6 meters, right? Because for 1 atmospheric pressure, the absolute vacuum is 10 meters, but the pump efficiency is about 60% or 70%. So you can draw down, right, the water up to 6 or 7 meters only. Okay. Now it's important, right? The drawdown, right, should be below the formation level. So for factor of safety, it should be about 0.5 meters, right? So you have, 0.5 meters, right, below the formation level. That is the absolute, right, dangerous level, right? Now for the groundwater table, suppose the sump, right, or the pump fails, what will happen? Well, the groundwater table will soon rise us up. Now that you may be danger, right, endanger, right, the people working in the basement site, right, or in that construction site. Because if the water level goes upwards, right, there will somebody may be drowned, right? 浸死啊. Okay. It's the liquefaction, right? The soil becomes liquefied. It's called the boiling, right? Or the liquefaction. Okay. Have, you know, a mixture of water and sands, right? Where you will get drowned, right? Drowned to death, right? So they are the dewatering, right? Sometimes we insert, right, the, you know, the barrier, right, to block all the groundwater table, right? But it's impossible to block all, right? Anyway, there will be some groundwater able to seep into the site. Then you have to do some open some or some pit, right? Some pit to pump any water seep into the, you know, entering into your site, right? Okay. And you may have some very physical cut-off wall, the ship piling, right? So you can see here, right? Okay. So, you know, the soil is less pervious, right? And if you dry the ship pile, right, into a less pervious layer, then you cut off the, you know, the groundwater table, right, on the, you know, behind the wall and in front of the wall. Well, for formation of roads, right, you can have, you know, you have either, right, the rigid pavement or the concrete. You have the flexible pavement. It's asphalt, right? Okay. 瀝青啊. Okay. Asphalt or concrete. Now, for the concrete paving slab, remember that there are two layers. Now, it should not, it's called the mesh reinforcement, okay? Mesh reinforcement, not the steel reinforcement, right? You know, and then is you got the concrete, right, here. And down below is a, you know, road base, right? Road base. And further below is called the subgrade, right? So the subgrade. Now, we always talk about, you know, the formation level for the road. It's the subgrade level, right? So above the subgrade level, right, it has to be very firm, right? You use the roller, right, to pass through several times. So you got a very firm subgrade surface first, and then you know, to put up the road base, right? It's the compacted gravels, right? And then finally you got your concrete pavement, right? So I leave it to you. Right? Now, what about for the flexible pavement? Now, again, you got, you know, usually it is the subgrade here. And that the other layer is what? The first layer, there's the wearing clause, right? The WC, right? The wearing clause. And then you have, you know, the row base, and the subbase. So you got, you know, three layers, right? The, you know, the subbase, right? So you got the WC, right? The row base and the subbase, and underneath is the subgrade, right? Now, of course, what's the asphalt? Asphalt is in fact, right? You know, in the concrete. In concrete, you know what's aggregates, right? And what's the cement. So these two, of course, you have to add water, right? But for asphalt, you got aggregate, right? And we don't have the cement for the asphalt, but we have the bitumen. So bitumen is the serve as a binder, right? Just like cement, right? To cement the aggregates together to form the concrete. Okay. Okay, for site formation, we do have some minor rows, right? Trunk rows, you know what's the trunk rows? Condo, huh? Okay, for minor rows, right? We have the concrete pavement, asphalt pavement, right? Of course, for the roads to put under construction traffic, of course, concrete will give you better performance. But for other temporary roads, we just use the bitumen, right? For temporary only, right? We don't need to, you know, to put very expensive concrete there, right? Because after you have done the construction, you have to break it into pieces, right? That will give you a lot of money, right? To break down a concrete road. So here we have the asphalt, right? Pavement, right? Bitumen or granular. So it's much, you know, a better and more economical solution for the temporary haul road system. Okay. Now that's end up my discussion for the chapter 6, right? Now I give you say 5 minutes, right, to have a break, and before we step into the assignment 6, right? Okay. So let's take a, you know, a short break here, right? Now, welcome back to the tutorial. Now, before that, please take a note of the announcement over your screen. Right? Submit the assignment 5 before this midnight. And also, you have to be careful about the naming of a file, right? The A file, and then your name and student number, please in a single file, right? In PDF format. Right? Otherwise, I will reject your submission. Right? Please observe the instruction as far as possible. Okay? And please take a note that the report guideline, right, has been uploaded to the Blackboard. And please also observe the deadline for the submission. Please take note, right? The individual lab report. So everyone has to have to submit his or her report only, right? Not the group report. Okay? Now, can you see the Word file? Can you see the Word file? Yes, okay. Now I will start the explanation, right? Or give you some hints, right, to do this assignment 6. Assignment 6. Assignment 6. First of all, okay. Now I believe every one of you should be able to work out the, right? Okay, you work out the pressure diagram, right? The active pressure diagram. So can you, right? So you got, you divide it into, right? Say the, F1. Here is the F2. And you got the F3, right? Now, in front of the wall, right? So you got, the passive, right? And that is, the active. Okay. And then you also have a water pressure, right? That's water pressure. Water pressure, right? And then you also have the water pressure here. Say that's U1, right? And that's U2, okay? And you got, the PP pressure, right? And then you have the tie rod here, right? Now, can you work out the take moment about the toe? About the toe, right? The T here, right? The toe T. So you can work out the overturning moment about the toe, right? Right? The moment about the toe, right? You got this value. Okay? Due to the F1, F2, F3, and F4, and also the U1, right? The U1. So the U1, okay? Work out the forces and also the lever arm, and they apply the moment, right? So there's no problem, right? And then the next step is to take moment. Now, the most important thing is take moment about the tie rod, about the tie rod. Now, what will you get if you take the moment about the tie rod? Sorry, it should be moment about, I make a mistake. Not about the toe, right? About the tie rod, right? So you measure, right? The distance between the F1 and the tie rod, right? And the distance between the F2 and the tie rod, right? So you got all these moments about the tie rod. Now, what about for the moment for the passive force, right? Under, the passive, right? Passive forces. Now, for equilibrium, right? For equilibrium, right? The MT, you got the MT already, right? Due to F1 up to U1, right? Now, can you work out the moment due to the passive resistance? It should be not only the passive, right? But also the U2, right? The U2 moment. Okay? So you can work out here, right? The moment of U2 about the tide level, right? And you got this, so you can able to work out is equal to MT, right? F1 U1 minus MU2, right? Okay? So what will the passive force will be required? Because you know the MP, right? So MP divided by what? The lever arm. This one, right? The lever arm L, right? Okay, L. So divided by L. So it gives you the passive flow required. Because this equation here, right? Right? Here, clockwise moment equals anti-clockwise moment, okay? So you can work out the passive force, right? The MP divided by the lever arm, so give you the passive force required, right? But do you know the passive resistance? Here the PP, right? The PP is the passive resistance. Okay? Okay? Now, it should be less than the PP, right? The passive resistance. And divided by 1.5, right? Because we have to adopt a factor of safety, 1.5. Right? Okay? Here's the factor of safety. Okay? Now the tension in the anchor. Tension in anchor equals to what? It's equal to what? You can see here, right? All the force anchor is pointing towards to the right, right? To the right. So to the right. What's the forces pointing to the left, like F1, F2, F3 plus U1, right? And here, pointing towards to the left is the what? Right? The passive force. Right? Passive force required plus U2 divided by 1.5, right? Okay? So, okay? So any question? Is that okay? Good. Now we come to the much more easy one, right? Much more easy one. The Q2, right? The question 2. Okay, now for this question, Q2, now you got, here, okay, you got, when the force of the anchors is towards to the left, so here's the passive pressure. So you can be able to work out the Kp, right? Right? And what about the behind, right? This anchor is the Ka, right? So what you got is here, right? You got this, right? The Fp, and you got, Fa, right? The active force. So if that is, that is 79, 79 Kn towards to the left. So plus Ka, sorry, Fa, Fa, okay, Fa equals to what? Fp divided by factor safety. You never use the full strength of Fp. It's the resistance. You can't rely 100% on the resistance. You have to adopt a factor safety, right? Even though the Fp could be up to, say, 150 kN, but you can't use the full strength 150, but use only 100. So divided by 1.5, right? that will give you a safe design, right? So is that okay? It's quite an easy one. Okay. Now we come to the question 3, right? Well, for this question, first of all, you have to identify, right? Soft to medium clay. So you have to, go over to the lecture notes, right, and find the PAC's recommendation, right? It should somewhat look like this. Okay. So you got here. Okay. So you got this pressure diagram, right? And then, okay, then you have here, and then you have here, right? Then make sure that they are the joint here, right? And then you pick out this one. You have to work out how many kPa are there, right? How many kPa? Okay. So there's A, B, C, D. Okay. So that's A. So you work out, right? Here, right? The hinge here, right? Say the RB dash, right? So can you work out, how many kPa? So you can use the moment principle, right? To work out, take moment about that point, you got, right? The RA and RB dash, right? And then the next piece, right? You got, right? RB double dash, and you have the RC dash, right? And then you got this one, okay? RC double dash, and sorry. So right, B dash, C dash, the RD, right? So what you have, how many kPa? You work out the how many kPa, and so the struck load will be equals to what? Right? So you work out the RA, and RB equals to what? RB dash plus RB double dash, right? And RC dash plus RC double dash, right? And of course, you have the RD. Is that okay? So is that clear? The left-hand side assume that is steep fissure, not soft to medium. Let me check. Question Q3. I see. It should be okay. Figures, refer to figure 3, to the figure, please. Okay. Not the question itself, right? Yes. Okay. So any question? Now we come to the end of our tutorial. Use point 4. So any question? Okay. Q2. Yes. So any further question? If no further question, I'll stop here. Okay. Question 4 is optional, right? Q4 is optional. It's up to you to, to give me the solution or not. Anyway, it's quite similar to the previous one we have talked about in the last tutorial. Okay? So bye-bye.